This video is about inverse functions. We would like to be able to do the following: find an inverse algebraically, verify inverse functions, sketch the graph of an inverse function from a given function. What are inverse functions? Well, inverse functions are functions that undo the original function. So if we think about a one-to-one function, and we must have a one-to-one function in order to have an inverse. So let's call this function f of x. And f of x is going to take a to b and c to d. Well, then our inverse function, which we use the notation f inverse of x, that's the way we read that, is going to take d back to a and d back to c and b back to a. So it undoes it. Now notice for the notation here that the f inverse notation is not the reciprocal of f of x. And not all functions have inverses, only one-to-one functions have inverses. So basically, an inverse function is a function that reverses or undoes the original. So what you should notice, and you may have noticed in previous classes, is that for our function f of x, this first set is the domain and the second set is the range. But when we look at the inverse functions, this is now the domain and this is now the range. So we're actually switching the domain and the range. And what happens there is we're just going to interchange the x and y variables. And visually or graphically, this is going to be a reflection over the line y equals x. So I have a couple of examples here. The first one is just a set of ordered pairs. If I have a set of ordered pairs, 4, -5, 3, 8, 5, 9, and 3.3, 6.4, all I have to do to find the inverse, so we would maybe call this H inverse, is to switch the x and y ordered pair. So instead of 4 going to -5, we have -5 going to 4. We reverse the 3, 8 to 8, 3, and so on. So all we're going to do there is switch the x and y coordinates. If we're given a graph, like we are on this second example, we can still take the ordered pairs that are indicated and reverse them. So rather than having 5, 3, we would have 3, 5. Rather than 2, 1, we would have 1, 2. Instead of 0, -3, we would have -3, 0. And then you'll notice -5, -5 just gets reversed itself, and we get this reflection about the line y equals x, because all we did was reverse the x's and the y's. So let's take a look at some other examples here. If a function is one-to-one, then its inverse is also a function. And again, we read this as f inverse. So I have two sets of ordered pairs here. I have -2, -7, which now becomes -7, -2. And you can see for each ordered pair, if this is my x value and this is my y value, we have just switched the x and y table, so we have an inverse. Notice for this example that this is not even a function. It is a function. -2 goes to 7 and 2 goes to 7. But if you think about that, we have -2 going to 7, and we also have 2 going to 7, f of x. But if I wanted to look at the inverse function, then 7 would not know where to go home. So we can't actually have an inverse here because this is not, it can be an inverse, it can be an inverse, but it's not an inverse function. Now, let me show you what we sometimes do when we have something that is not one-to-one. So for example, let's say we have f of x equals x squared. Well, we know, or we should know, that the graph of this is a standard parabola with the vertex at the origin, like this, and that this would not pass the horizontal line test. It would cross in too many places. So what we often do is we only consider part of this. So we might consider this function f of x equals x squared, but only if x is greater than or equal to 0. We call this restricting the domain. All right, so how can we tell if two functions are in fact inverses? Well, if they are inverses, when we compose them together in either direction, f of g of x or g of f of x, I should get the result of just x. And it turns out if one of those is true, then they're both true. So for example, if we have f of x equals 5x plus 8 and g of x equals x minus 8 over 5, and we want to show that they are in fact inverses, we just need to compose the two functions together. So f in this case is my outer function or my template, 5 times something plus 8. That something is this g of x, x minus 8 over 5. The 5's will cancel. We get x minus 8 plus 8, or simply x. So these are inverses. And we would just say g of x is equivalent to f inverse of x. We would just give it that name. Now, what if we are given a function and we want to find the formula for the inverse algebraically? Well, there are 4 steps here. The first thing we're going to do is replace our f of x with y. Then we're going to switch the x and y. Then we will solve for y, and then we will give it the inverse name. So we're going to start with this first example here. F of x equals 2x minus 3. And I am going to first replace the f of x with y. And then I will switch the x and the y. And then I'll begin to solve for y. So I will add 3, and then I will divide by 2. And then rather than calling it y, I will call it f inverse of x. And I'm actually going to write this as x over 2 plus 3 over 2. And then I wanted to show you what that looks like graphically. So for our original function, f of x, it's a line, and so we've got negative 3, and we will go up 2 and over 1, up 2 and over 1, up 2 and over 1, and we get this line for f of x. For f inverse of x, this function written in blue, we know that our y-intercept is 1.5, and then we will go up 1 over 2, up 1 over 2, down 1, back 2, and we will get this line. And notice that that is a reflection about the line y equals x. All right, here is another example. Again, we're going to assume a standard scale here. I want to determine if the function is first one-to-one. So we're going to graph g of x equals x cubed plus 2, which is the graph of x cubed shifted up 2 units. So we should have something that looks something like this. Is it one-to-one? Well, hopefully you can see that it would in fact pass the horizontal line test, and it is one-to-one. Since it's one-to-one, we'd like to find a formula for its inverse. So we'll replace the f of x with y. Then I will switch the x and the y. And then I will begin to solve for y. So in this case, I will subtract 2. And then I will take the cube root of each side. And I will call it f inverse. Oh, excuse me, g inverse in this case. So what does this look like? Well, this is a cube root shifted to the right 2. And it's going to look something like this. And again, this is in fact a reflection across the line y equals x. So I have a couple of more examples here. Pause your video and see if you can find the inverses here. Oops, hold on. So pause your video and I will write down the answers here, but see if you can do these too. For the first example, hopefully you got f inverse is x minus 3 squared plus 2 is the f inverse of x. I did want to make a note about this one. Because this original function has a domain that is restricted to x greater than or equal to 2, and our range is y is greater than or equal to 3, when we find our inverse function, we have to have this caveat here that our domain has to be x greater than or equal to 3. I guess I made a boo-boo when I wrote that. X has to be greater than or equal to 3, and the range will be greater than or equal to 2. Notice how they just got switched. The domain and the range got switched. So pause your video again and see if you can find the inverse function. So first find your domain and range of your function g of x, then find the inverse of g of x, and then note the inverse domain and range. Okay, so if we look at our original function g of x, you should notice that because we have 2x plus 1 in the denominator, that cannot be 0. So 2x cannot be negative 1, or x cannot be negative 1/2. So for our original function g of x, the domain is x cannot equal negative 1/2. And the range, unless we graph it, might not be as obvious. So we're going to leave that for now. When we look at g inverse, we notice that 2x minus 5 cannot be 0. So 2x cannot be 5, and x cannot be 5/2. So for this, the domain is x cannot equal 5/2. And again, the range may not be as obvious. But what we do know is that when we find the inverse function, the domain and the range get switched. So that must mean that this is y cannot equal 5/2, and this is y cannot equal negative 1/2. Just switching the domain and the range for our function and our inverse.